thank you for the invitation. I really appreciate the opportunity to speak a little bit about my work in the East African Rift. As you may know and be aware of, this is a culmination of a lot of people's thinking about these things, and I'm just going to highlight a few aspects that I think are kind of important or useful when we use volatiles in volcanic settings or in tectonic settings. So, oops, now I have to advance. Oops. Yeah. So if we look at the East African Rift, we have these very spectacular volcanoes there, and one of them's Nyiragongo Nyamuragira in the Congo on the western side of the rift. And that volcano is a huge emitter of volcanic gases and has been for a very, very long time. Simon Carn wrote a very nice paper now 10 years ago about the global emissions of sulfur dioxide. And this very active volcano always appears as a large emitter over the years. Now, another famous one, of course, is Lengai in the eastern part of the rift, and that's the world's only active carbonatite right now. And interestingly, Lengai is quite famous and spectacular, but we still don't have a very good sense of how much gas is emitted from this volcano. And that's because it's kind of hard to measure the emissions of gases from Lengai. So we have those two spectacular volcanoes, but let's look at Nyiragongo a little bit more and see what it tells us. Does it tell us anything about what's going on from a very basic, standard way of thinking about things? So we have passive degassing. So that means just emissions of, and I'm focusing here on CO2, but we have to realize that volcanic gases are a mixture of water vapor, carbon dioxide, sulfur dioxide, H2S, hydrogen chloride, fluoride, noble gases, hydrogen, methane, and so on, right? So it's a very complex mix of volatiles that is constantly coming out of volcanoes. But in order to go through this process a little bit, we focus on CO2. So we look at passive degassing, eruptive degassing. And eruptive degassing for CO2 is challenging to measure because you cannot measure CO2 by satellite reliably. So you actually have to know the carbon sulfur ratio to obtain the CO2 emissions from that particular volcano. And when you do that and use the passive plus eruptive degassing, you get a total emission of CO2 of about 4 megatons per year, which is very significant. It's kind of on the order of Etna in Italy. It's bigger than Kilauea. And, that's eruptive and passive together. So there's a large amount of CO2 coming out of this volcano. And what does that tell us? Does that tell us anything? Is that unusual? Where's that CO2 coming from? And one of the things that is always challenging when we're trying to understand the relationship between CO2 in the magma or coming out of magmas and the CO2 in the source of those magmas, we need to know the magma flux, right? We need to know how much magma is moving up across some boundary or across some level to degas that CO2 due to differences in solubilities at higher and lower pressures. All right. So if you have an idea of the magma flux, then you can get the amount of CO2 that's in the source that is required to produce that CO2 flux. And here is just an example. If you have a very high magma flux, you'd have a very low CO2 concentration in the source and so on, right? It's just a simple mass balance essentially. So unless you know the magma flux, you don't know the CO2 content in the source from the gas emissions. So we have to be clear about that. Now, well, do we know the magma flux? Well, it happens that we have an idea, at least, from Albino's work. And for that particular one volcano, the magma flux was determined to be, this number here. And if you plug that in, you get a CO2 concentration of 4,000 ppm in the source. Okay. Um, Now, if you believe that number or not, that's up to you. But that's what you would get. You'd have to have that much CO2 completely degassed from that magma flux to get the flux of CO2 that you measure at the source. And this method is very commonly used in volcanology and volcanoscience. And for example, there was a very nice paper by Anderson in Poland a few years back where they did the same thing for Kilauea. And what they did for Kilauea is a bit more sophisticated, but essentially they're also using a Kilauea CO2 flux, and then they model the magma supply rate to match that CO2 flux. And in these graphs, they just use two different time periods for Kilauea eruption, 2001 and 2006. And then essentially, if you have the magma supply rate, you can get the CO2 concentration in the source. And so for Kilauea, this would be about 1 weight% of CO2 in the source. Okay. Again, it's the same exact method that I just showed you, but this one is much more sophisticated, looking at how do magma flux and CO2 flux match in terms of the model. But in principle, it's the same. So the Niramura-Gira estimate is a bit lower than that, 0.5 weight%, right? 4,000 ppm. So you see that this is not unusual, right? Kilauea, Niramura-Gira have similar CO2 concentrations in the source. Now, if we look at Oldonyulengai, for example, Oldonyulengai has this estimate of carbon in the source that was so mantle carbon in the source that was about 300 ppm. Okay, so this now I have to go back for a moment. This is undegassed magmatic CO2 concentration, right? And that's in weight%. We then convert that to mantle carbon concentration. And you have to make this conversion of assuming that you have, 10% melt fraction and, the carbon CO2 conversion, because of the molar differences in weight, we can convert that, right? And that's what we got for Oldonyulengai, this estimate that we did back in 2009, which was 300 200 to 300 ppm in the source. And for Niramura-Gira, it would be here about 100 ppm carbon in the source, right? So that 100 ppm carbon in the source translates to 4,000 ppm CO2 in the melt that degasses, assuming 10% melting. Again, we can make this much more complex and use melts and get these numbers. But in general, that's what you would expect. Okay, so we see that for MORB, this number is much lower, right? MORB is about 80 ppm, and clearly we see that for Niramura-Gira and also for Oldonyulengai as well as Kilauea, we have more CO2 in the source than for MORB. Okay. And you may remember that or maybe you don't, and it's not important, but I just point this out that in the 2009 paper, we said that Oldonyulengai has a similar CO2 concentration as MORB. And we based that on a very similar calculation, and the result obviously was the same. But the thing is that MORB was considered to have higher CO2 content at the time. So the knowledge about mid-ocean ridge basalts, has changed a bit. So the 80 ppm at the time was a really low value. Some estimates went up to, the value we had at Oldonyulengai. So that's the kind of discrepancy that you see. At any rate, all of these volcanoes have higher CO2 concentrations in the source than MORB. Now, I don't know how much more time I have, but what I wanted to point out is that the bulk of the degassing in the East African Rift, besides near Muajira, happens along faults in diffuse settings, where um, the CO2 is released through faults. Okay,
You
and
just
hmm?
Tobias, you just got to 10 minutes, so you're good.
I'm at 10 minutes. Okay.
Yeah, so you have time. Lots of
Okay.
time.
Okay. So, we focus on the volcanoes very often because they're very spectacular and dynamic. So, but fault degassing is an important component in the East African Rift. And, we kind of stumbled upon this. We had a project and we wanted to measure springs, but there were so little springs that I decided we need to measure diffuse degassing. And we focus on this is in the northern part of the rift. I'm not going to talk about that, but I'm going to talk about Magadi and Natron Basin and the CO2 emissions along that part of the rift. And the but when you look at the CO2 emissions doing this diffuse degassing work, where you essentially have an instrument and you have a small coffee can size container that you put on the ground and you walk around and you make a bunch of measurements and then you do statistics and and then you calculate essentially a flux of CO2 coming off the ground, right? And that's this data here. From this campaign, it was, I think we made about 1,000 measurements or more during that particular campaign. So we have to realize that all of these are spot measurements and that they are extrapolated. And that's the best we can do right now. But what is striking, I think, is that first of all, we have CO2 fluxes from the Magadi and Natron Basin that are very different from the Manyara and Balangida Basin. So if we go from the rift, which is over here, that's Natron Magadi, onto the craton, the CO2 emissions really, really drop down. Okay. In Balangida, which is on the craton, still you have faults there that, we measure on the faults, but there's just so little CO2 coming out, as opposed to Magadi Basin, 10 times more, right? Or 10 times less. The other interesting thing is that what is the source of the CO2? Well, the source of the CO2 can be identified using carbon isotopes, and you just plot 1 over CO2 to get at the pure CO2, which would be 0 over here. And so clearly there's mixture with air. And then you have, though, a mantle-derived CO2 composition. And that's the mantle value here, around -5. And then as you go to Balangida and the stuff on the craton, the places on the craton, it's very light. So it's really dominated by organic carbon sources. And helium isotopes, again, are very useful in identifying the source of the volatiles. We see that Manyara Balangida are purely crustal gases. Okay, so there's very little gas coming out. The CO2 is mostly from the little bit of vegetation, and nothing is coming from the mantle there. I'm going to skip this guy. But what we see then is that also when you look at the geophysics, we see that the craton boundary would be here, and then here is the rift, right? And across this section here. Oops. And now if we plot it in the same way, we see that the helium isotopes are crustal on the craton. As we go to the craton boundary, we jump to 7 Ra, which is a mantle value. And then as you get further over, the values again go down because there's mixing with some crustal components. CO2 flux is very flat, nothing on the craton, and then you jump up to the craton boundary. And then as you go further away, again, it remains high, but it's dominated by these faults. So it aligns with this area of low density in that section of the rift. Okay, so the boundary is exactly where Oldonyo sits, right? So Oldonyo sits right at the craton rift boundary, and that's where you have the highest helium numbers and you have the highest CO2 flux. Now, this here could be, maybe that is the mantle depth of melting, perhaps, right? And I don't have time to talk about that, but essentially, um, well, let's skip this, but essentially, we came up with this model where we have the craton here, the thick Tanzania craton, and then we have the rift, and this part here is the carbon-rich part of the rift, where CO2 has been accumulating over time. This is from the paper with Steve Foley, where we calculated how much CO2 is being accumulated at the base of these cratons through gradual influx or through plumes. And and we see that you can accumulate massive amounts of carbon at the base of the craton, and then in this model we envision that this accumulated carbon moves laterally out and then essentially triggers melting, generation of melts that then rise up into the crust pond there and provide the CO2 flux. This is consistent with some identification of melt bodies in the crust in that region, as well as with the high CO2 flux. Whereas on the craton, you just don't get that CO2 emissions. You don't get these CO2 emissions because there's just no pathway. There's no melting happening under it to allow the CO2 being released at the surface. I think I'm going to stop here for conciseness. Thank you.
Awesome. Thank you very much, Tobias. So there's a question already in the chat um, from Yafet. Please, do you wanna mute your mic and ask the question? Yafet?
Uh, yes, hello.
Oh, yeah, we can hear you. Please go ahead.
Yeah. My question is, I see some CO2 measurement on the upper rift segment, Bandahararo and Dabaho, and I was wondering if they are from literature or if those data are solid measured one.
Those are measurements that we made there with Bernard Marty and Raphael Pick's group. And that was a while back, but we have not yet published that data.
Good to know. I am a student of Raphael Pick, and we have more data to add, so it's good to know.
Great.
Great.
Awesome. I have a follow-up question. Well, do we have any other question for Tobias? And please, if you have a question, just raise your hand and I will see that in the chat. Tobias, a question. So I've always wondered if we have other conduits for volatile degassing from this rift other than faults, such as carrier beds, permeable sedimentary unit, which often dip towards the border fault, dip predominantly in a certain direction, unless you have a graben where they dip in opposite, you can have them dip in opposite directions. So I wonder if there's any under accounting for volatile fluxes in these rifts, because we're just not identifying those, fluxes that are going into certain thick, permeable, porous, syn rift sedimentary strata in the basins. Do you have any comments on that?
Yeah, I think that's a great comment, Folarin. It's what we have done was make transects across places, and with James, he has mapped the faults really well, and
Right.
we found these correlations in the field where the flux was really highest around the faults, and once you get away from them, you don't see much of a flux unless there are also some springs, right? So springs are usually also associated with faults to some extent.
Right.
And so generally, we think that it's mostly along faults, but you raise a very important point that if you have these sedimentary structures you could potentially bring the CO2 up and then accumulate it somewhere
Exactly.
below the
Exactly.
surface. And it doesn't mean that it makes it to the surface, but it's still coming off from the mantle and we
Right.
just don't see it. So
Right.
that's a really good point.
Thank you.